And yeah, the recording has started. So Xavier, the floor is yours.
Okay, so thank you very much for the opportunity to tell you about a joint work that we did with Emo Welser from Zurich. And so it's about order types. So let me just give you the pitch, what I'm going to tell you about. So if you don't know what order type is, let me just say right now that it's basically a combinatorial object that is induced by a set of points. So in RD in general, but I'm mostly interested in what happens in the plane. So for us, an order type or a labeled order type is a combinatorial structure induced by a finite point set in the plane. And one thing I would like to do is to do some random generation of order types. And I would like to make this random generation not necessarily completely uniformly, but at least I would like to avoid excessive bias. I would like to see order type as diverse as possible. And I don't know how to do that. So what I'm going to tell you today is why some very natural methods for sampling order types are very inefficient. Okay, so that's the pitch. I don't provide solutions. I'll end up with questions, and the number one question is how could we possibly generate random order types efficiently and without too much bias? Okay, so of course, feel free to stop me if there is any question. It's much easier to answer them as we go, and I'll be happy to. If there is any question in the chat, I will, by experience, not see it. So anybody who sees it, please.
I can take a look at chat. That is
please.
Good. Yeah.
Thank you. Okay, so what are order types and labeled order types? It's something that was initiated by Eli Goodman and Ricky Pollack, and who both passed away. So Ricky a few years ago and Eli a few months ago. And the reason they looked at that was the following. So Eli said they were basically looking for the simplest possible geometric object something interesting could be said about. Okay, and they ended up with order types. So let me just go through the very, very basic version, which is what happens on the real line. So in one dimension. Assume you have a sequence of points, P1, P2, P3, etc. to Pn. So each one is a real number. They are not necessarily sorted. So there is an underlying combinatorial information, which is every time I give you two indices, I and j, you can tell me whether Pi is smaller or larger than Pj. Okay, and based on this information, what you get is the order of the points or a permutation of the points, right? And we're going to do the same thing in higher dimension. We're also going to do something which doesn't make quite much sense here, or at least is not so interesting. We're going to identify all those orders or permutation up to relabeling of the points. Okay, so of course, if we relabel the points, there's only one equivalence class we can end up with in the line. And it turns out that in dimension 2, the structure gets much more richer, much more intricate, and these are basically labeled order types. And so one way to define them is to basically introduce what's called the orientation predicate, which is just the generalization of the pairwise comparison that we saw on the real line. Okay, and given a triple of points, so an ordered triple of point, the orientation is just a map that assigns it a sign that is -1, 0, or 1, depending on how the third point is positioned compared to the line through the first 2 points. Okay, one way to think about it is if you are standing in A and looking at the line 2B from A to B, does C stand on the left side, in which case the value is 1, the right side, in which case the value is -1, or on the line, in which case the value is 0. And let me you can also talk about the orientation of the triangle from A to B, B to C, C to A. Is it counterclockwise or clockwise or flat? And flat won't interest us throughout. From this point on, I will assume that all the points that we are dealing have no aligned triple. That's what's called simple point sets. Okay. And when you have this notion, it's very natural to consider that if you have two sequences of points, the P1 to Pn and Q1 to Qn, And the only information you have access to are orientations of triples, then if every time you take 3 points with indices I, j, k, you get the same answer for the pi and the qi, it's very natural to identify them. Okay, and that's what the notion of labeled order type does. 2 point sequences have the same labeled order types. If every time you take the orientation of 3 points from the one sequence, you get the same answer as taking the orientation of 3 points from the other sequence with the same indices. Okay, and of course, this is an equivalence relation, and what we call really a labeled order type is an equivalence class. And you can think of this as, you can represent this either by an actual point sequence, one of the representative of the equivalence class, or you can also represent this by a map that sends for every triple of indices, it tells you +1 or -1. Okay. And if just to give some example, if you're looking at size 4, these are the 14 possible order types. And as you can see, they split up into 6 order types, 6 labeled order types where the points are in convex position. And each time, of course, you could label the point differently. You could apply a circular permutation of the label, and you would end up with the same labeled order type. And there are 8 where the point form a triangle with a point inside. Okay, and already here you can see that giving up on the label, which is what we do in the next step, there will be some different treatment that will go on depending on the shape of the points. Okay, so now a natural question you could ask is, given a map, does it encode a labeled order type? And there are some very elementary necessary conditions that you can list. For example, there is some action of the symmetric group. You can permute the points, and you will flip the sign every time you do a transposition. And there are certain local consistency rules that you have to comply with that can be phrased on up to 5 points. For example, if you have a point D that is inside a triangle, then it will imply certain condition on the orientations. But actually, besides those rules, so these are all necessary, and there are no simple necessary and sufficient condition, and we have little hope of finding some, because solving this problem, this is a decision problem that is actually NP hard. Okay, it's not NP complete. We don't even know if it's in NP, but it's NP hard. It's actually worse. It's ETR hard for those who are familiar with the ID. Now, a second question is how many labeled order types are there? And here, the best answer at the moment is that bond here, n to the 4n plus little o of n. Okay. And this is much fewer. So this is roughly 2 to the 4n log n. So that's much fewer than all the choices you could have here. Okay, that would be 2 to the n cube. And the reason why there are so few, relatively few, is because this is some kind of algebraic structure. It's an instance of a semi-algebraic hypergraph. And underlying those semi-algebraic structure, there is a theorem by Milnor and Thom and others before, but it often goes by the Milnor theorem, that tells you that the number of sign patterns that you can get from a certain number of polynomials is much fewer than the 2 to the number of polynomials. Okay. And why do polynomial enter? Well, orientations are actually signs of determinants, of 3x3 determinants in the plane. So those are 2 aspects of the structure. It's hard to describe combinatorially, and it is really very algebraic. Okay. Now, coming back to labeled order type, one thing we might want to do, especially if we do discrete geometry, is to drop the labeling and say, well, there are these 14, they're actually divided into 2 different situations: 4 points in convex position or triangle with a point inside. And this is just a slightly different equivalence relation where we identify point sets. The sets are not ordered anymore if there is a bijection that preserves orientation. Okay, so in other way, two sets have the same order type if there is a way to label them so that the labeled sets have the same labeled order types. So this is really letting the set of permutation act. And we can see here already for 4 points, we get at least 2 different classes. So things get more interesting on the line.
Xavier, sorry, I have a
Yes.
question.
Yes.
Is this equivalence relation the same as, so you can also have in 2-point sets, you can ask yourself, can you deform one point set into another so that for each triple of points, the orientation is always defined. So it's never zero, they're never at the same line. And you can say that 2-point sets are equivalent if you can do that.
Yes.
Is this the same relation or not?
No, no,
Okay.
it's not. It was actually open for quite a while, but the answer is no. So let me just come back to that.
Yeah, I thought
slide.
you were gonna talk about it, but you didn't
Yes.
do it. So okay.
Yeah. So the answer is definitely not. Okay, and so let me fast forward. The answer here is given by Mioff's universality theorem, which tells you the following: you can fix the order type, or say the labeled order type, and look at all possible endpoint sequences of endpoints that realize this order type. Okay, and you can, on this set of realization, you can ask what is its topology. And the question you just ask is, for example, is it connected? If it were connected, the answer would be yes to your question. And what Mioff proved is that actually this set can be arbitrarily complicated. It can have the same homology, the homology of an arbitrary semi-algebraic set.
I see.
Okay, so the number of connected components is arbitrary, the fundamental group is arbitrary, and so on. Okay, and that's a very different picture, because if you look at those necessary conditions that I mentioned before, they can actually be given a geometric meaning, because you can define order types as soon as you have a structure of a topological affine plane, meaning a notion of lines. Okay, so what you need is that any 2 point define a line, and any 2 line intersect in a point, and as soon as you have this projective structure, you can define a notion of order types. And the labeled abstract order types in this model, they are actually a well-known structure in optimization. They coincide with the acyclic uniform-oriented matroids, and those are computationally pretty simple. Okay, in particular, deciding membership, I give you a function that tells me for every triple of indices, does it turn left or right, and there is a polynomial algorithm to decide if this comes from an acyclic uniform-oriented matroid. And this universality of Mioff, that tells you that when you stick to the affine geometry of the affine plane, this becomes much more complicated. And in particular, deciding this question is as hard as deciding the emptiness of a general semi-algebraic set, okay, which is what this ETR completeness means. Now, we still know a few things on order types. So in the case of realizable order types, we know how many there are up to size 11. Even for size 12, we have no idea. Okay, and so these bounds here, they are obtained while identifying mirror images. Okay, so they are actually essentially half of the number of order types. Okay, and in general, there is no bound, no formula for the number of abstract or realizable order types of size n. Okay, so we don't know. There's a lot that we don't know. And in particular, you can see here that the number is actually, I mean, it grows faster than exponentially. So the number of order types of size 12 is probably very, very large. And although here we have a complete tabulation of all the order type up to size 11, it looks like this cannot go on for a long time. Okay, if you're interested in order type of size 15, presumably we're not anytime soon going to give you a complete list. Okay, so now it would make a lot of sense to be able to sample those space of structures, and this is what I'm going to talk about now. Okay, so question is, given n, how could we possibly generate a random, say, labeled order type, or label or unlabeled of size n? Okay, and there are these two different reasons. So three reasons. First, we might just be curious how to do that. It turns out that the standard methods in particular in analytic combinatorics for random generation they cannot, they don't apply to other types. So from a purely academic point of view, it's really a reasonable question. It's something that requires new ideas. But moreover, if we want to test problems or conjecture that depend only on orientation predicates, for example, there is this theorem that tells you that the empty convex Kegen theorem. If you have a set of points in the plane that is large enough and no tripole are aligned, then there is always 6 points that form an empty convex hexagon. Okay, so this is an hexagon, but it's not empty. This is an empty hexagon. And such an empty hexagon is guaranteed to exist as soon as n, as your number of points, is large enough. Okay, and for hexagon, large enough means, well, there is a proof that I could follow that says it's at most 1700 and change. I saw that there was some announced better bound of 900, but I could only find a source in Russian, so I don't know. I couldn't understand, so I was conservative here. Maybe this bond is a bit better. Maybe you can get it to 900, but the best example we know are size 29. Okay, and so if you want to go fishing for lower bound for constructions, it's reasonable to sample point set. But in fact, this only depends, the fact that points form an empty hexagon only depends on the order type. So you don't want to keep sampling the same order type again and again by sampling your point sets, right? And another reason, if you want to do some testing on geometric algorithm, right, some random testing, checking that the algorithm, all the branches are sound, you don't want to test the same trace twice. And so that means that what you really want to try is not necessarily random inputs, but random set of values on predicates. And so if your only predicates are orientation, then you want to sample random order types. Okay, and there are really two natural ways to approach this question of generating a random order type. First, what you could do is try to construct a random map, random orientation, and then you're going to produce a random labeled order type. That's fine for me. But also you could try to construct a random point set and read off its order type. And both of these problems, they hit some rock, right? First, if you try to build a random map, well, we saw that very few maps are actually labeled order type. And secondly, it's very hard to decide, given a map, if it is. Okay, so generating a random map like this by, for example, flipping triangles and things like that, it will be very hard to remain inside the world of maps that correspond to labeled order types. Now, if you take a random point set, so first there are some theoretical results that tell you that there exist some points, there exist some order types that will require an exponential number of bits in any representation. But we don't know if those order types are too numerous. So let me not take this as an objection, but still you can try taking a random point set and you can look how well does it do. And so this is something we did with some colleagues, and we took 1 billion subsets of 10 points in the unit square, which we put, say, the square between 1 and 2. And we take random floating points with pseudo randomness that is reasonable, so Mersenne-Twister random generator. And we just look for those 10 point subsets. How fast do we discover the 28 million or so order types that exist? And it turns out that 1 billion sample reaches only 10 million of them. Okay, and the last million sample get you only 2,000 new order types. Okay, so it's going to take a while to get the 18 million more order types. And moreover, the speed at which you discover new order types is really decaying. So, and at this point, when you've thrown these 1 billion samples and you've seen only 1/3 of the space, you've seen at least 500,000 times the same order type. The most popular showed up more than 500,000 times. Okay, so this is really a very redundant way to produce random order types. Okay, and so this is where the result that we obtained with IMO shows up. What we showed is if you proceed like that, there's actually a theoretical guarantee that it's going to fail. Okay, because the data I showed you is only for 10 points. So maybe it gets better as n increases in theory. But in fact, no. What we show is that when you sample points in a square, for any n, there is a subset an of the order types that is very small. So the cardinality of an becomes negligible compared to the number of order types. And as n goes to infinity, the probability that the random point set that you get as order type is an in an goes to 1. Okay, so there is a subset of the order type that is combinatorially, it weights less and less, it goes to 0, it goes to a proportion 0 of the order type, but you hit it with probability going to 1. So this is what we call some concentration result. Okay, so how do we get that? We basically get this by analyzing random polygon, random convex polygons, and comparing a classical model of random polygons, which is what people in probabilistic geometry have been studying for half a century. You take a set of points sampled independently from a measure over RD, and you take the convex hull, and that gives you a random geometric object, which is a random polygon, a random polytope, actually, in dimension D. And you can do that. Well, you can take a measure that is uniform on the square, uniform on the disk, uniform, Gaussian distribution, anything you want. Many different models have been studied. And in our case, we look at a slightly different model where instead of taking random points, we take a random order type chosen with equiprobability among all order types of size n. Okay, and we look at the extreme points. So for n equal 4, there are only 2 of them. So that's 3.5, this average. For n equal 5, the answer is 4. And our main result is that as n goes to infinity, the average number of extreme points you get in this combinatorial model is about 4. Okay, and it turns out that in these geometric models, the number goes to infinity. So let me look at it in a bit more detail. Most of the type have few extreme points, as I said, just because you can apply Markov's inequality, right? So the number for the type with at least e extreme point, the proportion is at most 4 over e. But let me look at the random variable that is counting the number of extreme points in various geometric distribution. If my points are in a square, that the expectation of the n is of order log n. Okay, better bounds are known, but I'll stick with the big theta. That will be enough. If the points are taken in a disk or actually in a smooth convex body, you get n to the 1/3 on average. If you sample according to a Gaussian, you get square root of log n. Okay, so in all cases, the expectation goes to infinity. Moreover, in all cases, people could prove some concentration bound. So what they proved is that the variance, which could in principle be up to the order of the square of the expectation, is only of the order of the expectation itself. Okay, and no, that means this is enough to get us the concentration, because you define an to be the set of order type with at least half of the average extreme points. And now by Markov's inequality here, the proportion of order types that end up in an goes to 0. Okay, because e goes to infinity. And the probability that now a random point set does not land in an, well, for that you need the number of extreme points to deviate from the average by at least half. Okay, and there you can apply Chebyshev inequality, and because the variance is small, that goes to 0. Okay, so as soon as we get this result that most order type have few extreme points, we will get this concentration bound. Okay, so let's see how. So this is our main result. Given for any n, if you take a labeled order type uniformly among all, then you get the number of extreme points is on average this, and variance at most 3. Okay, and the average here, it's an exact formula. And we can extend this result for non-labeled extreme order types. Okay, and we get a less precise bound. It's this. And we can generalize to arbitrary dimension, to also the abstract model. So in the abstract model, in the labeled case, we still get the same bound. In the non-labeled case, we get something coarser. And I'm going to give you a few ingredients on the proof. First, the idea is to average the number of extreme points over well-chosen subsets of order type. Okay, so I'm going to explain each of these ingredients after that. Then each subset, we will represent it by a symmetric set of two endpoints on the sphere. And we're going to use duality to relate those projective order type to arrangement of great circles. And we are going to relate the average number of extreme point, okay, in those subset here to basically the average number of edges in this arrangement, which is what shows up here. Okay. And when we want to go to non-labeled order type, we have to account for symmetries. Okay, so now I'm going to go through these 4 steps one by one. Okay, so far so good? Okay. So what do I mean by averaging on subset? So, and this is what I'm going to tell you is the first idea that Imo told me over lunch in Mexico, right? When he said I can do something, and his idea was the following: take a simple endpoint set in the plane, and here I take them in convex position, you know, but it can be anything. And now let us take some line L that splits the point set. So there are points of A on both sides of L. And now let me apply a projective transform that maps L to infinity. I end up with this picture here. Okay, and my line L now is at infinity. And I apply any projective transform that does that, right? There are many of them, but I don't care which one. I end up with a new point set A prime, and also a bijection between the points of A and the points of A prime. And it turns out that in this bijection, there is some constraint I can express on whether a point is on the convexal of A or A prime. And actually, so I could actually take now a line in A prime that separates it and send that line to infinity and end up with A, right? So this is actually a reversible transformation. And now, the fact is that A and A prime, they share via this bijection at most 4 extreme points. Okay, there are at most 4 extreme points in A, whose images are also extreme in A prime. And the reason is, to be extreme here means that there is a way to move the line at infinity to touch one of the points without sweeping over another vertex. Okay, so your vertices should touch this green zone, which is just the region you can sweep by a line without going over a vertex. Okay, and if you transport this region, it's a union of lines, so a projective map will transport it, and it will transport it in this funnel here. What are the vertices in this funnel that can be touched by a line without going over a vertex? Well, only those, and that are already on the convexal, well, only the vertices of the 2 edges that L is intersecting. Okay, so that's at most 4. And so that means that in principle, we have a strategy, right? We could now try to match order types so that any pair in the matching is related by a projective transform. And then on every pair, the number of extreme points sums up to at most n plus 4. And so on average, we get at most n over 2 plus 2. Okay, it's not 4, but it's not n. Okay, and if we want to go that way, well, we have to go through quite some hoops, right? We would need to actually articulate the matching. So we're going to do something actually much simpler. We're going to divide up the order types into classes, where actually a class is just all the order types you can get from a given order type by these projective transforms. Okay, so I'm going to divide them into buckets, and each bucket will be all possible projective images of one single affine order type. And then we're going to average the number of extreme points in each bucket. Okay, so what are our buckets? Well, let me spell it out on this example with 5 points. So I first have this order type with 5 points in convex position. Okay. And now, of course, if I apply an affine transform, nothing will change in the order type. So the only thing that really matters when I try to apply a projective transform is how does a line that is sent to infinity divide the point set? Okay, so I could divide it into 2 plus 3, in which case I end up with this order type. Okay, just think of these points being sent at infinity very far up there. Okay, so they will form a convex quadrilateral with this point inside. I could also take this blue line here that splits 1 and 4, and then I get this, right? This point is sent really, really far at the bottom, and so these 2 points and the one at the bottom will be extreme. Okay, I know there is a very convenient way to think of this. It's to map, first, we could map the plane to an open hemisphere just by this standard projection from, I put the plane tangent at the North Pole and I project from the center. Okay, and then this defines a bijection between the plane and the upper open hemisphere. And now let me complete the hemisphere and add the symmetric of the points. Now, sending this line to infinity to get, say, the red line, to put the red line to infinity, is like saying that, no, I'm looking at this is now my equator, and I'm looking at the points in a hemiset. And what I obtain is a new order type, this one. Okay, I could also take this blue great circle and look at one of the hemisphere it gives me, and I will get this other order type. It doesn't matter which hemisphere I take. There's a central symmetry, so it will be just the same order type. Okay. So instead of thinking of one order type on all its projective transforms, we can actually think of a symmetric order type on the sphere and all the affine subsets it contains. Okay. And when I speak of a symmetric order type on the sphere, what I have in mind is actually that orientation of triples of points, they are actually recast as the signs of the determinant of the triples of vectors. So I can also define equivalence class for point sets on the sphere, and all the terminology of order type carries over. Okay, so I'm now going only to talk about this. So I will start with an affine point set. I will take its projective closure, and I will look at all the order type of a fine subset that I find in this projective closure. Okay, and of course, it turns out that there will be some multiplicity showing up, right? Actually, this point set, this set of 10 points, there are 2 different ways to cut out a hemisphere that to obtain a hemisphere that will give you 5 points in convex position. To get 4 points with a point inside, there are actually 10 ways to do this. Okay.
Sorry, you count oriented hemispheres?
I count, yes. So I really count hemispheres.
Yeah, that's what I meant.
So 2 opposite hemispheres count twice. Yes.
Okay, thanks.
Yeah. So these 2, those 5 points and those 5 points are the only 5 tuples of points that can be selected by a hemisphere and form this order type. Here, you basically have to choose how you split, 2 and 3. So you can take 2 here and 3 there. And there are 5 different ways to do that up there. And you can also take 3 up and 3 here and 2 there. So, depending on which hemisphere you take, what is you get a factor 2 on the same here. 4, 1, and you have to choose the hemisphere. Okay. So now that we have this, we can clarify this idea of duality. So we have now our projective set of 2 endpoints. And we are working with hemisphere, right? And so hx is open hemisphere centered at x. I want to take my hemisphere open. That will, if anything confuses you, that might be because you're allowing antipodal points. That I don't want that to happen. And now as x moves, a point enters or exits if and only if as that point on x become orthogonal vectors on the sphere, right? So it's really that tells us that we should perhaps look at the dual hypergraph, at the dual arrangement, sorry, of these points, meaning for every pair of antipodal points, I look at the great circle of vectors that are orthogonal to this pair. So I have two endpoints forming n pairs, so I get n great circles. And now I get exactly n points in my open hemisphere if and only if my point x is not on one of those great circles. Okay. So x, I will take it inside the two cells, the two-dimensional cells of this arrangement. Now, if I take 2 points x and y in the same cell, well, I can move from x to y without becoming orthogonal to any of the two endpoints. So that means that hx and hy will select the same subset of points. Okay. And a point is extreme in one such subset if and only if the great circle of this point, so the great circle dual to this point, appears on the boundary of the two cells, meaning forms an edge of the boundary. Okay, that means you can move the great circle in a way that this point is the first one to exit. Okay, and so that means that the affine subsets that we can read of this projective set, they're really in bijection with the two-dimensional cells of the dual arrangement. So far, so good? Okay. Good. So now, now the trouble starts showing up, because now every affine order type that you can read off from P, so that is in the set of projectively equivalent order types that P is representing, P is our projective set, it corresponds to one, but possibly several two cells in the dual arrangement, because there are many different ways you can select points in P and get that order type. So let's mu omega denote that number. How many different ways can you find order type omega in P? When you average the number of edges over the two cells, you're basically averaging the number of extreme points in those order types, but you're weighting that average by how many times each order type appears. Okay? And so this term on the left, it's very easy to compute, right? It's a basic averaging on the arrangement. You have n great circles. It's a simple arrangement, so no three great circles go through the same point. So you have exactly 2 times n choose 2 vertices, because any pair of great circles intersect in 2 points. Every vertex is of degree 4, so you get twice that many edges. And Euler's formula gives you that you have 2 n choose 2 plus 2 faces. And so the average number of edges per face, that's 8 times n choose 2 divided by this. Okay, and that's about 4. So this is exactly the bounding main result. It's the average number of edges in an arrangement of n great circle in general position. So the question is how, so this is this value. Now we need to control the multiplicities. And we're going to do that in a very different way in the labeled cases and in the unlabeled. So in the labeled cases, there is some magic that happens. Okay, some miracle occurs. Let us run this thought experiment. Let us fix some set of 2 endpoints on the sphere and do 2 random generations, or actually just one, but okay. Let's sample an affine subset. Okay, so we take a subset of P, meaning we choose a 2 cell of the dual arrangement uniformly at random among all 2 cells, and we get the affine subset corresponding to that. Then that subset, we label it uniformly at random. So we have n points, so there are n factorial way to label it. We pick each one with weight 1 over n factorial, with probability 1 over n factorial. And then we return that labeled order type. Okay, question, what is the distribution on those labeled order types? There are 2 sources of bias, right? First, A is not uniform among all affine order type of affine subset that you can find in P, right? The order type of A is not distributed. We saw that if P is this set here, there are two subset A that will form 5 points in convex position, 10 where you get 4 points plus a point inside, and 10 when you get a triangle. So those two will be more likely than this one. Second, some unlabeled order type, they may decompose into more labeled order type than others. So we already saw that earlier, right? When 4 points in convex position give rise to 6 different order types when you label them, and a triangle with a point inside gives rise to 8 different order types when you label them. That means that the condition of the probability that A is a square, each order type has a probability 1/6. And here, each order type has a probability 1/8. Okay. And it turns out, and this is a rabbit out of the hat, that those two biases, they cancel each other out perfectly. So let me illustrate this on a simple example of computation. Let's do this for 5 points, and let's compute the probability that your A bar is exactly this labeled order type. So you can decompose this as this conditional probability, right? And this is easy to compute. So the probability that A is 5 points in convex position, well, there's 22 different EMI sets, and only 2 of them give you 5 points in convex position, so you get 2/22. And condition on that, out of the 120 different labelings, only this one on its 5 circular permutation will give you exactly this labeled order type. Okay, so the answer is this product. Now, if I do the same computation for this configuration, again, same probability, conditional probability, so here I get 10 out of 22. But here, because I no longer have a symmetric configuration, I only get one possible labeling. And you see, these two are equal. So what happens here? What happens is that the symmetry of the projective point set and the symmetry of the affine subset, they interact. Okay, so a symmetry is just an orientation preserving bijection. So of course, naturally, symmetry forms symmetry groups. Okay, they're closed under composition, and you could think of, if you look at this affine set, for example, you can have a cyclic group as a symmetry group. If you go to projective set, you can have possible dihedral groups. Okay. And it turns out that these symmetries of a projective set, they act on the affine subset. If you take so those symmetries, they are not at all geometric transformation, right? They're just combinatorial maps that sends points to points. But we don't make rotations, but we require that those combinatorial maps, they preserve orientation. And it turns out that they actually preserve being the intersection of the point set with open hemisphere. Okay, so these symmetries, they act on affine subsets. And that means that, in fact, when we look at our projective set and we fix an affine subset, we can look at the orbit of that affine subset under all symmetries of the projective set. And it turns out that this is exactly all affine subset with the same order type. Okay. We can look also at the stabilizer. What are the symmetries that keep an affine subset globally invariant? Okay, that maps it to itself. And this is actually the subset of those symmetries from a subgroup of G that is actually isomorphic to the symmetry group of the affine subset. Okay, and the reason is for those two properties is that basically symmetries, they preserve orientation and so order types, and they preserve antipodality. They have to. That's something easy to show. And then when you have an affine subset, you get exactly 1 point from every antipodal pair. So the symmetry restricted to an affine subset determines completely the symmetry. And so if you work with those 3 IDs, it's very easy to get those 2 things. And now there is this orbit stabilizer theorem that tells you that whenever you have a group that acts on a set, the product of the size of an orbit with the stabilizer of that set in that orbit is always the cardinality of the group. Okay, and the orbit here, it's basically proportional to the probability that A has a given order type, right? So that this is the source of our first bias. This is the source of our second bias. And the product is independent of A. It only depends on G, which comes from the projective point set P. Okay. And so that's how we get our first result. So again, this is the average complexity of a two-cell in an arrangement of great circles. And this actually is the zone theorem, by the way. You take a simple label order type rho bar uniformly at random. So with this uniform distribution, you read off the underlying projective order type. Okay. You analyze the number of extreme points of rho bar conditioned on the value of tau. And that's the averaging argument on the great circle. So you get this bound. And this is independent on tau. So in the total conditional probability, that's the result you will get. And that's it. Okay? So far, so good? Okay. So now at this stage, how much time?
As much as you want, essentially. So
okay.
We have another talk at 6. So in that case, you could still talk for an hour if you want.
Okay.
But I guess if you want some questions afterwards, then
yes. Okay. Yes. So let me. I'm going to sketch at a much higher level what follows now. What happens if we drop the labeling? Well, we lose this magic compensation because we basically have two sources of bias and they cancel each other. But the second source comes from the labeling. So if you drop the labeling, you no longer compensate for the first source of bias. Okay. And so this source of bias is basically the ratio of the number of symmetries of the projective set to the number of symmetries of the affine set. And those can be different for different subsets, right? If you have 5 points in convex position, you get 5 symmetries. If you get 4 points with a triangle inside, you get 0 symmetries. You just one, I mean the identity. Okay, so this ratio is what we have to account for. These are the weight. And so the natural question is, how are these two quantities related? What can those ratios be? And in fact, more fundamentally, how are those groups related? Okay, so we already saw that this is always a subgroup of this. Can we say a bit more? And more generally, what can this symmetric group be? And so that's what we clarified. So it's actually not so difficult to get the classification of the symmetric groups of affine sets. So it's always trivial or a cyclic group where the number of symmetries divides n. And the reason is that basically your symmetries, they will map the convex hull to the convex hull. And they will map the second layer to the second layer. Because if you drop the convex hull, that becomes the convex hull. So it has to act on every layer independently. And so it has to divide the number of symmetries has to divide this here.
So what exactly do you mean by layer here? Sorry.
Okay, so what I mean is what's called onion layers usually.
Okay.
So the first layer is the vertices of the convex hull.
Mm-hmm.
The second layer is a set of vertices that are on the convex hull once you remove the first layer,
mm-hmm.
and you keep going. Okay. And every symmetry has to induce a permutation, a circular permutation of each layer.
But that might be true for other possible definitions of layers as well, right? So
yes.
two key layers and stuff.
Mm. Yes, okay. Yes.
Okay.
That would be, yeah.
I see. Thanks.
And there's a catch. It could be that you have actually 1 point left alone, in which case you could divide n minus 1. Okay, because you apply the same to the set with n minus 1. Okay. And this classifies completely the symmetry. Of course, my examples here are very geometrically regular. So I draw things on concentric circles, but it doesn't have to be, right? It's a combinatorial symmetries. The points need not be, those symmetries need not correspond to rotations. Now, if you look at symmetries of a projective set, there's actually a property that is not at all obvious at first, is that every symmetry of P fixes exactly two opposite emisets. So if you think about a geometric rotation, right, an element of SO3, it's actually going to fix 2 points. Your rotation will have an axis of rotation. The 2 points there will be fixed. And also the upper hemisphere and the lower hemisphere will be globally invariant. So in our case, the two, what's called the poles, the 2 points where the axis of rotation intersects the sphere do not make sense in the combinatorial setting. But the 2 hemispheres that are globally fixed, those they exist even at this combinatorial level. So that's actually not trivial to prove. And one of the ingredients that was quite surprising is that we could prove that every orientation reversing bijection, so if you take a map from P to itself that reverses every orientation, there has to be a great circle that contains every point that is mapped to itself and that separates every point from its image when a point is mapped to something else. And you can prove that every orientation reversing has to have orbits only of size 1 or 2. Okay, so the orbits of size 1 have to be on a great circle, and the great circle has to intersect every segment joining points in an orbit of size 2. Okay, and that's something we get from Adverger's transversal theorem, which was a bit unexpected in this setting. Now, since we have this, that every symmetry of P fixes exactly 2 hemisets, we can go back to Klein's characterization of finite subgroup of SO3. And the way Klein's proof works, so it basically looks at how those symmetries act on the poles, so on the fixed points of the rotations. But it doesn't really, you could go through his proof and replace poles by globally fixed hemisphere. It would be the same, right? It's a set of size 2n, antipodal, and so on. So we can just go to his proof and unfold it in this setting, and it goes through up to some point. So up to what point? Well, we managed to get the type of orbits, meaning for the action of those groups on the hemisets, how many orbits do we have, and what size are they? Okay, we get a complete classification of this. And from that, we have to work a bit more. Okay, so we have to account for symmetries. We managed to get the average number of extreme points as a function of the number of symmetries. We managed to argue that any point set with more than 60 symmetries has an affine hemiset with actually at least half that number of symmetries. Okay, and the number of affine set with many symmetries we can control. Okay, by carefully counting sign patterns of polynomials. And putting all this together, we managed to go back to this averaging formula and get rid of those mu, omega, the weights, the multiplicities of the order types. Okay, so I'm not claiming I give you a proof, but these are the key ideas we have to use in the proof. Okay, and in fact, along the way, we can actually characterize what are the possible groups. And there are, so the trivial group is possible. You can have a cyclic group. You can have a dihedral group. You can have the octahedral, the tetrahedral, and the icosahedral group, which means you can actually have all the finite subgroups of the rotations. Okay. And each of them, so these are the only one you can have, and each of them, they actually can be realized. So for each of them, we could find a point set that has exactly that symmetry group. So it's interesting that you get exactly the same result in this combinatorial setting as you would have with rigid rotations. Okay. So that's all the technical details I wanted to share. Let me just give you everything we couldn't do and we would like to do. First, we have these conjectures that, so we could prove that for certain models, we had some concentration, and we conjecture that this holds much more generally. The weaker version of the conjecture is that as soon as if you sample points identically, so you take IID points from some distribution in the plane and you rid of their convexor, then and you rid of the order type, then what you get should be concentrated, in our opinion. Okay, we cannot prove it. If you remember the proof that I went through, we use two facts. We use that the expected number of extreme points goes to infinity, and we use that this number was concentrated, sufficiently concentrated. So we conjecture that the concentration is really not essential here. And we actually believe that sampling points identically is hopeless. And one indication why this could be the case is that if you oversample, say you actually aiming for an order type of size n, and you take an order type of size n plus 1, and then you drop 1 point at random, you don't get a uniform distribution on order type of size n. Okay, so let me spell it out on order type of size 4. So if you want an order type of size 4 and you go for size 5 and you drop a point at random, well, this will always give you 4 in convex position. Here there is if you drop this point or that point, you get a triangle with a point inside. On any of the other 3 points, you get 4 points at random. And here you can do the computation, okay? And when you sum them up, you get that this guy shows up with probability 0.6 and this guy with probability 0.4. And this phenomenon, we believe, is actually amplified, right? And that's why taking points that are identically distributed doesn't seem to be such a good idea in general, but we can't prove it, of course. So another natural question is there any good way to produce random order types? So what do I mean good is, I would like to spend a time that is polynomial in n for each sample, so polynomial time delay. And I would like the bias to be reasonable. Say no order type shows up more than a polynomial number, polynomially many times on another one. Is there a question or?
I don't think so.
Okay, I saw some, so I guess.
Okay.
Mistake or good, but not a question. Another natural question is to go beyond the extreme points. So more precisely, what do typical order types look like? So this tells us on the outer layer, so what happens on the next layer, how many points do you have on average, and so on. How many layers do you have on average? We don't know. And for now, our techniques cannot deal with that. And last, when looking at these projective order types, we found some relaxation of the Erdős-Székely theorem. So Erdős-Székely tells you if you have sufficiently many points, you can always find k in convex position. Okay, and it turns out that if you take an order type, so you can phrase this as it is very hard to avoid. It is actually impossible to avoid k points in convex position. Similarly, it is very hard to avoid a triangle with a point inside, because the only order type of size n that avoids it is n points in convex position. Copenhagen-Jerusalem theorem tells you as soon as you have a point inside, there will be a triangle containing it. And more generally, you could ask, if I give you a fixed order type, is it true that the fraction of order type that avoid it goes to 0 as n goes to infinity? So the size of the pattern is fixed, and now I look at sets of size n, and I wonder, is it true that most of them will contain it? And we could prove it for any pattern that has this form. So you take a triangle and you make a convex chain on one of the edges. Okay, and this is just by applying the Erdős-Székely in the projective order types that we get this. And so more generally, it would be interesting to find this. This is, if you go back to the permutations, this is true. This is a Marcus-Tardoš theorem, and it was conjectured by Stanley and Wilf. So there are some other combinatorial model where this phenomenon occurs, and it's natural to ask it for other order types. And I'll shut up now, and if you ask questions, if you have any.
Sorry, I was muted. Yes, thank you very much, Xavier, for your talk. Do we have any questions?
I have some random questions. Okay. Hi. Yeah. So. Yeah. Yeah. I think it's the first time I've seen this sort of thing, but I was wondering about something. So, is there something you can say about order types if you like say, for example, you're in the plane and you assume that like all your quote unquote randomly chosen points they come from like some kind of specific subset, like some arrangement of curves in the plane or something?
No.
Okay.
I mean, besides the trivial, right? If your curve is is convex or so, but no,
Okay.
it's actually, I don't know, if you fix a curve, how many different order types can you get?
Yeah. Okay.
Yes, I think that would be very interesting to know, because so the bounds that we manage to get on the number of order types, they come from an algebraic argument, which basically says an order type of size n is determined by 2n variables. And so you look in the space R to the 2n, and you write the orientation conditions, and you get a certain number of polynomials, and you count sign conditions. Now, the number of variables is really a critical parameter here.
I see.
And if you manage to, if you could describe, I don't know, interesting subsets where they can all be drawn with points on a curve, that means you can represent them with using one coordinate per point, plus some constant number to describe the curve. And so you would manage to get much tighter bounds on the number of order types.
Yeah. Thanks.
All right, do we have other questions? So I actually have one, and it's about the random sampling. So, I mean, one way that I would think maybe I would do random sampling after hearing this talk is to sample points uniformly on the sphere, or like projective points, look at the arrangement, and then pick a uniformly at random cell from the arrangement and write down that order type. So how bad is this? Do you know? Have you tried this?
Yeah, so first, the average number of extreme points in that model is constant.
Yeah.
So that is
that's a good sign.
Yeah. And second, when I ran this experiment on subset of size 10, you get actually up to 24 million. So in a billion experiments, you get, instead of reaching only 10 millions of the points, you reach 24 million out of the 28.
Okay.
So it's much better. And also the most frequent order type, instead of having 500,000, you go to 4,000. So it seems to be much better.
Okay. So experimentally, it's much better. Probably not perfect, but
probably not perfect. But definitely, if you're running experimental search for this or that conjecture, it's definitely worth running it with that kind of models. It really samples the space of order types quite differently.
Okay, nice. Are there any other questions? If not, then I actually have a second. Sorry, so I'm just gonna jump in there. So for the last conjecture that you had with these kind of forbidden subconfigurations, so if you think about the question that you said in the beginning with the empty holes, that wouldn't fit in that framework, right?
No, because it also depends on the rest of the point set.
Yes. Is there any way of phrasing that conjecture also with empty? Because I mean, there's this empty convex polygon thing for 7 doesn't work anymore because of Horton sets, right?
Yes.
But if the point set is large enough, then I guess the Horton sets are a very small fraction of those. So kind of, but any generic set might still have a 7-hole. That could.
So you could revive those K holes for larger K by.
Has this been done? Do you know?
No, not that I know of.
Interesting.
Yeah, no, I don't know how you could do that. That's interesting. Yeah.
All right, thanks. Any other questions? If not, then well, thank you very much again, Xavier, for nice talk and nice answers.
Thank
I
you.
will stop the recording now.